right on time. I think we're ready to go. It's 8 o'clock. So.
Okay, so should I start?
I think so. Yeah, please. Thank you.
Okay. Okay. Good morning, everyone, and welcome to this exciting course on hydrogen as an enabler for renewable energy. My name is Sturle Pedersen, and I am chairman of Greenstat in Sri Lanka. Today's course is part of its newly established Center of Excellence educational program. And the Center of Excellence in Hydrogen's vision is to share technology, insights, expertise, and experience in the hydrogen domain, and to support capacity building in Sri Lanka. This is the first course, and the second seminar that we are going to hold is already on the 16th of November. So after this session and speech, then you can sign up on our web pages, and you go then to greenstat.lk, and this course is also free, so don't miss this opportunity. I'd like to introduce today's speaker, which is Oda Marie Ellefsen, who has been working at Greenstat as project manager at our office in Norway. And she is very dedicated to advancing sustainability energy solutions. Oda holds a master degree from the Norwegian University of Science and Technology, NTNU. And she is extremely passionate, as I said, about the subject we are here to discuss and present today, green hydrogen. Throughout this course, we will embark on a journey to explore the incredible potential of hydrogen as a clean and efficient energy carrier. We will also look at the very basic and unpacking the fundamentals of the hydrogen molecule, understanding the hydrogen value chain, and also clarifying essential terminology like efficiency and energy density, some buzzwords that you have heard and which Oda will explain for you. But why hydrogen? Why is a topic of such a paramount importance in today's world of energy? To answer this question, Oda will get into it, but let me provide you with some context. Hydrogen as an energy carrier has the power to change the way we produce and store and utilize energy. It actually offers a very elegant solution to some of the most pressing challenges facing our planet, reducing carbon emission, increasing the integration of renewable energy sources, which is today quite a challenge, and mitigating climate change. During the course, you will also learn about the flexibility of hydrogen, how it can be harnessed to store excess renewable energy, excuse me, and how it can fuel a wide range of application, from transportation to the industry. We will also discuss or present the groundbreaking concept of green hydrogen and its potential to create a sustainable and efficient ecosystem. Furthermore, we will explore the role of ammonia as a hydrogen carrier, its application, and the exciting opportunity it's present for a future of green energy. And this is also quite important if you are looking at it in the context of the huge offshore wind resources we have in Sri Lanka. As we venture into the course, I encourage you to embrace your curiosity and engage actively in the discussion and the activities. Together, we will not only uncover the scientific and technical aspects of the hydrogen, but also examine the broader implication for the environment and society. In closing, I want to emphasize that our journey is just beginning. Hydrogen has immense potential, and together we will be exploring how it can be harnessed to create a more sustainable and cleaner future for the generation to come. So let us start and embark on this adventure, ignite our curiosity, and discover the remarkable world of hydrogen. I am confident that our collective efforts will lead to new insights and inspiring ideas and deep appreciation for the incredible possibilities that hydrogen offers in our quest for a greener and more sustainable world. Thank you again for being part of this course, and let us start this fascinating journey together. And the floor is yours, Oda.
Thank you very much, Sturla, and very inspiring start to the presentation. So I'll just go ahead and share the screen, and hopefully you can all see it now. So yeah, before I start the presentation, I want to thank you to Sturla for introducing. As you said, I'm a project manager in Greenstat in Norway. Worked in Greenstat for a little over 2 years now, and I joined the team because I wanted to work closer to the green transition. And Greenstat is really a green transition company. Our slogan is to make green happen, and we work every day to find ways of making the change from fossil fuels to renewable and zero emission energy faster and better. So our main focus area is hydrogen, green hydrogen, which is the topic of today's presentation. As you can see here, we also work with solar and wind energy, primarily to produce hydrogen through electrolysis. And since nothing happens in isolation, we also have to work with other aspects of the value chain from the primary energy to the end use. We have a large portfolio of projects in different stages. I wanted to highlight some of our flagship projects in Norway that focus primarily on hydrogen for maritime transport. So together, these 3 projects in Glomfjord, Rørvik, and Kristiansand will produce almost 9 million kilos of green hydrogen every year to supply ferries, container vessels, bulk cargo ships, and aquaculture workboats with zero emission fuel. And this will start in 2025. So we can't really discuss hydrogen without delving into some interesting theory. I believe there are some scientists in the audience, so I hope you're all familiar with the periodic table. Hydrogen is located at the top left, and it's the smallest, the lightest, and most abundant element in the world. So it's the first element in the periodic table and has been assigned atomic number 1. And in its electron shell, there is 1 electron. And that means it would like to have 2. And to do that, it will essentially bond with almost any other element on the periodic table and itself, which is why we usually find hydrogen gas as H2. It will bond with carbon to form different hydrocarbons. It will bond with oxygen to form water. It will bond with nitrogen to form ammonia. And that's the way we find most of hydrogen on Earth. So hydrogen as a gas will burn in air with a faint blue flame. It's very hard to see in daylight, but if you turn down the lights, it will have a faint blue flame, and it burns to form water. It's flammable at around 4% volume in air, and that's why we have to handle it correctly and with safety precautions. So 75% of the total mass of the universe is hydrogen. And the sun is about 50% or 57% hydrogen. And the way we get energy from the sun is that hydrogen atoms fuse to form helium and give us radiation here on Earth. So I'm sure if you've ever heard of hydrogen recently, you've heard about the different colors. And there are many different colors for describing ways of producing hydrogen. Like it's a colorless gas, but we use color to differentiate between the way we produce the hydrogen. So green, blue, and gray are the main types of hydrogen production that we work on. Gray hydrogen is produced through natural gas reformation, and in this process, we always have CO2 emissions, about 9 kilos of CO2 for every kilo of hydrogen produced. It's the primary method for producing hydrogen today. About 96% of the world's hydrogen production is through SMR, as it's called, so steam methane reforming. Now, the way some companies are working now to reduce the impact, the emissions from steam methane reforming is through carbon capture. And then we call the hydrogen blue. So we capture the CO2 that's produced in the process and store it or use it for other purposes. And that yields a lower carbon emission hydrogen that can be used for sustainable purposes. Water electrolysis using renewable energy sources is the most renewable way of producing green hydrogen today. There are no CO2 emissions either during production or during use. But of course, this requires that the renewable energy that we use is renewable. So in GridSat, we only work with green hydrogen today, and only work on electrolysis. So I'm going to spend the most time on this, and I'll go in a little bit more detail on the process there. Before I do that, it's important when we talk about hydrogen to know we refer to it as an energy carrier, not as an energy source. An energy source is basically a form of energy that exists in nature and hasn't undergone any transformation. Unfortunately, the direct utilization of these energy sources is quite challenging, and we have to go through some conversion process. So sunlight is an example, or uranium is an example. Coal, oil, and natural gas can also be characterized as energy sources. An energy carrier is produced from an energy source and stores energy that can be used later or at a different location. Batteries is an example of this, but so are hydrogen and ammonia that we'll talk about today. So, green hydrogen and electrolysis. The most important components in this is the electrolyzer and the fuel cell. So in water electrolysis, you split H2O, so water, into hydrogen and oxygen using an electrical current. So we are converting electrical energy into chemical energy in the form of hydrogen. So without going too deep into the theory, in principle, it's quite simple. You have two electrodes, a cathode and an anode, that are immersed in a container of water and with an applied voltage. The electrons will move from the anode to the cathode. And in this process, the water molecules will split, and the hydrogen atoms are attracted to the negative cathode and the oxygen atoms to the positive anode. So a fuel cell is basically the opposite of an electrolyzer. It uses hydrogen and reacts with oxygen from the air to form water. So in this process, we produce electrical energy to power electric motors or different devices. And as you can see, there are no emissions of either CO2 or NOx from this process. So there are many different electrolyzer technologies, and I won't go into all of them. I'll just mention a few. And alkaline is the most, I'd say, traditional technology for hydrogen production. It's very mature. It's been used in the chemical and metallurgical industry for over 100 years. It's extremely reliable and has relatively high efficiency, meaning that you use less kilowatt hours or electrical energy per kilo of hydrogen that you produce. The investment cost for alkaline electrolyzers is lower compared to some of the other technologies, and it operates at atmospheric pressure. That means that we will require additional compression work if we have to pressurize that hydrogen to store it or to use it. The purity of the hydrogen that is produced is also a little bit lower than some of the other technologies. So if we were to use the hydrogen in a fuel cell, we would actually need to purify the hydrogen further than what you get out of the system as is. And finally, it's also larger in size than some of the other technologies, and it consumes more space. So that's something to keep in mind, especially if you're low on areas to put your electrolyzer. An alternative, which is a twist on the pressure on the alkaline electrolyzer, is pressurized alkaline electrolysis. So it's an alternative. It's very similar to the alkaline electrolyzer, except that it operates at 25 to 35 bar, which helps us reduce the downstream compression work. It has the same efficiency as an alkaline electrolyzer, but it's also a little bit more responsive. So it will operate easier in systems where you have fluctuating energy supply, such as if you were to connect it to a solar system or a wind turbine. Other than that, it's pretty similar to alkaline. Now, the proton exchange membrane electrolyzer, or PEM, is a newer evolution of the hydrogen electrolyzers technology. It's different in that it transports the protons, so H plus ions, through a membrane, which is the proton exchange membrane. It's a polymer, basically, that allows the protons to go through. And it operates about at a higher pressure, so 15-30 bars, again, reducing the downstream compression work. And it's very suitable for variable inputs of renewable energy. However, it does use iridium and platinum as catalysts generally, which is why the capex, or the investment cost for this type of system, is higher. And currently, we expect shorter lifespans of the PEM electrolyzer compared to an alkaline system due to the membrane degrading over time. And finally, it's a lot more compact than alkaline electrolyzers due to higher current density. So it's smaller and more easy to put in a tight space, to put it that way. So energy chains and value chain and energy density. I want to mention this. It's important to, when you're designing a solution to convert a fossil system to a renewable system, to think about the energy value chain, which is the path that energy takes from primary source to an energy form that we can use for practical purposes. So in each energy transition, there's a transfer from a source to receiver, and the energy also changes its form. As in this diagram, the sunlight is converted to electrical energy through the PV solar panels. And then we convert that electrical energy to hydrogen through an electrolyzer, and then we again compress this to be used in the hydrogen refueling system. So you have to expend some energy there as well. So what I would like for us to be aware of is each step in the value chain where the energy is transferred, the energy quality is also reduced, and it's crucial to understand that operating with a short energy value chain is possible, is very wise. So if we can avoid any step in this process or shortening the chain here, we have a more efficient system. So here we have the energy value chains for compressed hydrogen and liquid hydrogen, just to showcase the difference between the two. In both cases, we have the production of the hydrogen. But to produce compressed hydrogen, we just have a compression step. We might have a transport step, which does use some energy. We store it, which doesn't expend any energy. And then we have the refueling. If we were to use liquid hydrogen, we'd have the production and the liquefaction, which is very energy intensive as well. The transport and the storage, we have the issue of boil off during storage and transport, where the liquid hydrogen basically boils and you lose some hydrogen in the process. And you have to regasify the liquid hydrogen to use it in a fuel cell. So that's also an energy expenditure. So that's just an illustration. I hope that's relatively clear. Moving on to energy density, and I'll be discussing storage a little bit later. But I want to show this figure for volumetric versus gravimetric energy density. So that's the energy per volume or per kilogram. And you can see hydrogen, either liquid or compressed, in the bottom right corner of the figure. And as you can see, the hydrogen has very high gravimetric energy density compared to most of the other substances. So it's providing a lot of energy for its weight. However, hydrogen is a gas. It has a very low volumetric energy density compared to the other substances here. So it's very important to keep in mind, both for transportation and storage. And it's also why it might be advantageous to produce green ammonia or other carriers from the green hydrogen that we produce. And another way to illustrate this, here we have 60,000 kilowatt hours represented in marine diesel oil, the volume that we require of marine diesel oil, ammonia, compressed hydrogen, and as batteries, essentially. And each box is 1 cubic meter. So as you can see, compressed hydrogen would require about 180 cubic meters of storage versus 18 for marine diesel oil if you were to use it on a ship. So again, you can carry less volume of or carry less hydrogen for a given volume than you can with fossil fuels. And when you look at the alternatives such as batteries, you have to consider that you probably can't carry all of the energy you require in a battery, depending on the application. So I mentioned green ammonia. There's a lot of talk about this in Norway, and I think also all around the world. And to understand why we talk about green ammonia, it's, I think, good to understand the Haber-Bosch process. It's an industrial process to produce ammonia from nitrogen and hydrogen. So if the hydrogen is coming from green hydrogen, so renewable hydrogen, the produced ammonia is green as well. And it's named after the two scientists who developed it, Fritz Haber and Carl Bosch, two Germans with, well, interesting history. But the Haber-Bosch process essentially involves mixing nitrogen from the air and hydrogen in a reactor, which operates at relatively high pressure and temperature, about 200 atmospheres and 400 to 450, I should say 450 degrees Celsius. The catalyst uses is iron, which helps lower the activation energy for the reaction and increase the reaction rates. And in the reactor, the ammonia gas is formed and then partially condensed into a liquid, separate from the rest, and then the process is repeated to produce more ammonia. So for each cycle, about 15% of hydrogen and nitrogen is converted into ammonia. And with the continuous recycling, about 98% total conversion is achieved. And this process is one of the world's most important industrial processes. It's used to produce fertilizer and food. So it's expected to play, but it's also expected to play a significant role in future zero emission societies. So we try to differentiate between the use cases for hydrogen, ammonia, and methanol to some extent versus batteries. And the way we tend to see things fall down is that batteries are used for short and small light vehicles. So personal EVs is an example. We have many of those in Norway. They're becoming more and more common in other parts of the world, and as small pleasure crafts at sea. Whereas hydrogen will be used when the application and the energy demand is higher. So that's for long haul trucking. It's for buses, ferries, workboats, and some smaller ships. And ammonia, methanol, those types of energy carriers will be used for really long distance shipping, deep sea shipping, and for carrying large amounts of energy in a sustainable way. So to look at the different types of storage solutions that exist, I'm not going to go through all of them, but just give you an overview. We have the compressed form of hydrogen, which is the simplest, I think, and most common. We have liquid form of hydrogen, and we have the different types of chemical storage solutions. So compressed hydrogen is stored in tanks made of either steel or composite materials. So both types of tanks must withstand very high pressures, generally about 350 bars, but some go even higher, 700 bars for vehicles or passenger vehicles. So weight can be a very important parameter in this context. As a rule of thumb, traditional steel tanks consist of about 80 kilos of steel per kilo of hydrogen, while composite tanks are lighter and consist of approximately 22 kilos of composite materials per kilo of hydrogen. These tanks often have a plastic liner as the inner layer to prevent corrosion. And just to mention, generally the composite tanks are made from carbon fiber, but there are some companies who develop glass fiber as an alternative. It's slightly heavier, but it's also cheaper. So, which is why it's starting to be used more in hydrogen storage. So, liquid hydrogen can be suitable for storing large amounts of hydrogen. So these storage tanks are highly insulated with vacuum insulation. They have an inner and outer tank, and they require some quite sophisticated materials. The hydrogen has to be contained at minus 253 degrees Celsius, which is extremely cold, to be liquid. So if you release the liquid hydrogen, the oxygen in the air can also freeze from this temperature. There's a ship in Norway called MF Hydra, which was produced by Nordled. It's a ferry essentially in India and Milan, and this is operating currently on liquid hydrogen, so it is possible to use also for fueling. Another thing to be aware of in storing liquid hydrogen is boil off. Some of the hydrogen will inevitably evaporate, but how much really depends on how long you're storing the tank and in what conditions. But we have to consider that if we're designing for liquid hydrogen as well. Now, ammonia and methanol are considered chemical carriers of hydrogen, and they have to be converted back into pure hydrogen generally if they are to be used in a fuel cell. They can also be used directly in some internal combustion engines. A company called Wärtsilä is exploring the conversion of or basically retrofitting of existing internal combustion engine to use a blend of ammonia and marine or maritime diesel in the engine. So the advantage is both ammonia and methanol are liquid at atmospheric pressure and relatively manageable temperatures. So they are very common industrial chemicals. However, they are toxic, both of them. And ammonia is also very corrosive. So that needs to be designed for when considering these alternatives. Another one I want to mention is called liquid organic hydrogen carriers. It's not very well known yet, but it's another method for storing hydrogen in essentially organic oil. This oil has an affinity for hydrogen and can be loaded with the hydrogen produced through electrolysis. And then you can transport the oil, the LCOH, the LOHC, sorry, to the end user, which can be a vessel or any other hydrogen use. And the oil is unloaded with releasing the hydrogen, basically, and yeah, you can carry the hydrogen is released and the oil can be reduced later and regenerated with and loaded with more hydrogen, so it goes in a cycle. So the oil is stored at room temperature and atmospheric pressure, so it's very safe and very low low engineering demand on the system here. Yeah, hydrogen and use cases. As mentioned, I mean, hydrogen's role in the energy transition is to be a clean and environmentally friendly alternative to fossil fuels. And it can replace fossil fuels in some industrial processes, but it can also be used as a fuel in transport sector. So potential applications include heavy-duty transport, buses, some construction equipment, and also normal passenger cars, though there are some limitations on using it for normal EVs. Railways is an alternative where normal electrification isn't feasible. And some people are also considering using hydrogen for airplanes. And just to clarify, a hydrogen car, truck, bus is essentially an EV where a battery is combined with a fuel cell and a hydrogen tank. So the hydrogen works as a range extender to the battery EV. And the hydrogen is not used in an internal combustion engine. It's used as in a fuel cell to drive the electric motor. Yeah, and the same goes for ships. Maritime transport, it's an area where hydrogen and ammonia and methanol can be used as alternative fuels to replace marine diesel oil. We can use either compressed hydrogen or liquid hydrogen, which is the case for this this ferry that you have on the slide. And currently there are two ways of using the hydrogen, either in fuel cells, which is the most efficient way, or also is being developed use in direct combustion, so in a internal combustion engine. So the ship here that we see, or the ferry that we see here, is running on liquid hydrogen. As it happens, there is no liquid hydrogen production in Norway currently. So the hydrogen is shipped from Germany to the coast of Norway in order to bunker on this ferry. But it is operating, and it's as far as I've heard, working well. Finally, globally, almost all hydrogen today is used in industrial processes, mostly for ammonia production, as I've talked about, also in refining of oil and in methanol production. And I just wanted to show some examples here, just to give you an idea of the size. These are two plants in Norway, one ammonia plant run by Yara, which produces 400,000 tons of ammonia every year and require about 70,000 ton of hydrogen per year. So they are currently working on replacing their gray hydrogen with green hydrogen with a pilot project. And here's an Equinor. Equinor is the largest oil producer in Norway. They also produce methanol here at Kjellbergodden, about 900,000 tons, which requires 110,000 tons of hydrogen per year. And finally, just to mention a little bit about the byproducts. During electrolysis, we generate obviously hydrogen, but we also generate oxygen. And finally, also generate some heat because of the inefficiencies in the system. So the oxygen and the heat represent essentially byproducts from electrolysis that we can use for other purposes. And the idea here is, in each of our projects, we try to think of ways to use these byproducts, both because they can improve the financials of the project, but also because it would be a reasonable way to increase the overall system efficiency. So if we use all this energy to produce only hydrogen, then some of that energy is basically lost. Whereas if we utilize the heat and the oxygen, we can get a much higher use of our input energy. And this is the idea behind industrial symbiosis. So we try to create collaboration between other businesses nearby, and we try to, for instance, sell the heat to district heating systems, or for greenhouse heating. In Norway, it's quite cold, so most of the year, so it makes sense. And the oxygen can be used in land-based agriculture, which is a big industry in Norway, and it can be used as a direct input in industries that require oxygen, so in some chemical industries, for instance. So this is something we work a lot with in our projects to try and realize best possible sort of energy efficiency of the overall system. Like I mentioned, the energy chains that we talked about earlier. So I think that's my last slide. I think I talked for quite a while. I hope there are some questions as well. Yeah, if you need to reach out, you can always do that. And I see there's a hand up, actually. Oh, Sturle.
thank you very much, Uda, for this presentation. I'm sure that there is someone who has some questions. I just want to comment on the NORLED, the hydrogen ferry that you had mentioned. If you want to hear more about it, you should sign up for the 21st of November. Then the project director for this project, he will be talking about it. It's a Dr. Ivan, who then will go through some of the challenges they had through this project. This is the first and only hydrogen liquid ferry in the world, so there is a lot of lessons learned. And of course, supply boats, tow boats, fishing boats, and so forth. There is many different projects that also the Greenstat is involved in, which hydrogen can be an efficient fuel to use as well, but you need a lot of energy. So I just wanted to say that, and then there is one thing that which was not addressed also today is biomass, which is of course Sri Lanka is an agriculture country and has a lot of biomass as well, and we will have one of our partners will have a session later on about this as well. So we cannot cover everything in one session, but I think this was an excellent presentation and walk us through all the different aspects in the value chain. So thank you again, Uda, but now we are opening the floor for the other people to ask questions, and would I pass on the word to you, and so you can take the questions.
Thank you, Sturla. Yeah, and thank you for your comments. Yeah, it will be a very good symposium in 2 weeks, so I encourage you all to sign up for that as well. To do that, and please do sign up for the seminar next week on the 16th. We have invited faculty from the Western Norway University of Applied Sciences, HVL, we call it in Norway. So, and they have run hydrogen courses for a few years now, and I'm actually a graduate from one of their courses. So they have some very talented speakers there. It'll be a session basically over 4 hours, with a more deep dive into technical aspects of green hydrogen. But it is meant for non-technical people as well. So it's very good course, and it's free. Normally these courses are quite expensive, so I do encourage you to sign up. If you have a chance, you can find that on the greenstat.lk website. We have a question here. Which are the planned locations in Sri Lanka for hydrogen-based projects to be developed by Greenstat, and with which partners? So Greenstat is currently conducting a national feasibility study for the government of Sri Lanka, and I'm sure if Sturla is still here, he can add to what I'm saying. But we are conducting feasibility studies on several locations in Sri Lanka, based on likely offtake scenarios. So either in both maritime and land transports. Want to add some details, Sturla?
No, I think that was kind of covering it. We are looking at the maritime, which is a key because of Sri Lanka's strategic location as well. And since Sri Lanka has a mission to export green ammonia or hydrogen or its derivatives, it will be important to have the infrastructure in place. 57% of the CO2 in Sri Lanka is related to transportation. So we are working with Ashok Leyland and the Lanka Ashok Leyland to make sure that the industry here can be on this journey for transition to the electric and hydrogen buses. So that is something that we will announce later. And we are working with the Lanka Oil, which is a subsidiary of Indian Oil, to set up the infrastructure for the charging and the fueling stations, because infrastructure is the key. And then we are also working on other projects for developing electricity in areas which currently are not well covered by the grid, to create new industries and jobs, so that can be part of improving the livelihood. We are also looking at the transportations between India and Sri Lanka, and of course ferries and other passenger boats that can go between the two. Tamil Nadu is one of the more ambitious and dynamic states in India as well. So I think there is several things. Some of the partners and so on, and some of the projects that we are doing is not disclosed yet, but we will do that in the near future as well. I hope that we cover it, but there is plenty to do. So we are inviting everyone to participate in this collaboration to bring Sri Lanka in the forefront. Thank you.
Great, and I think there are actually some more questions in the Q&A. So what is the water quality needed and the associated efficiency? So the water quality needed for electrolysis is generally quite high. You have to include demineralization or distillation systems to get the water quality that you require, because impurities from the water will degrade the electrolyzer. But that is part of the engineering of a hydrogen plant is finding a suitable water source and also purifying this water so that it can be used. The energy cost of purifying water is not that high. It's very low compared to the energy cost of the electrolysis itself, which is 55, 60 kilowatt hours per kilo. You might have to add one or 2 kilowatt hours for even if you do desalination. So it's not the energy cost that is the issue generally. It's more just engineering an appropriate water for the electrolyzer so that we don't get premature degradation of the electrolyzer. So I hope that's clear. There's also a question: what is the LCOH? So Dilip answered the question there. It's the levelized cost of hydrogen, and what it is. I mean, it's the cost at which we can reduce the hydrogen, and that depends entirely on if you're doing electrolysis. It depends on the cost of your electrolyzer, and it depends on the cost of the power or the energy, the electricity that you can get. So the reason why solar energy with hydrogen is being developed so intensely in places like India and around the equator is that widely available solar energy is generally cheapest. So even if the availability of your hydrogen plant is lower, the cost of the electricity is really important. And in Norway, we have hydropower, which is relatively cheap, at least in a European context, and it's also available 24/7, which is why Norway does have an advantage in developing hydrogen projects. So yeah, the levelized cost of hydrogen is going to range. Currently, most projects are in the $5 to $8 per kilo range. It really depends. But the goal for many is to get to maybe $2 per kilo long term, and then that's through cheaper electrolyzers, and it's through cheaper electricity costs. So those are main two drivers. So yeah. There's another question. What is the lifetime of PEM? So we generally think that we have to change the stack after 10 years. So, but it will depend on how the electrolyzer is operated. But yeah, 10 years is generally a appropriate stack lifetime. But you can replace it and then run for another 10 years without any issue. So that's what we use.
A little bit of comment on that, Oda. As you said, it really depends a little bit, but the 50 to 60,000 hours is today kind of the average. And there is work going on, and it is expected that is going to reach 100,000 to 110,000. Many of the energy systems today is then set up in a way that you can shift the stacks and you can kind of maintain them, and then you can get additional 40,000 hours out of them. So there is a lot of very positive R&D going on to improve the efficiency, durability, maintenance, better maintenance that can extend the lifetime of the assets and the key components, and maintain the efficiency, which is, of course, the most important.
Yeah, indeed. Thank you, Sturla. So there's another question in the chat. How does the carbon footprint of green hydrogen differ from that of conventional hydrogen? So conventional hydrogen, I think by that you mean gray hydrogen, which is, yeah, the most conventional way to produce hydrogen today. So considering that the emissions per kilo of hydrogen, the CO2 emission per kilo of hydrogen for gray hydrogen is about 9 kilos per kilo. And in practice, if you have fully renewable energy in your green hydrogen system, your CO2 footprint is close to zero. There are some emissions related to the production of the electrolyzers and to some transport, and I mean there are some emissions with every process, but the goal is really to be as close to zero as possible. So it's a significant gain in switching from fossil to renewable hydrogen from a CO2 standpoint. Okay. Can't see any more questions. So, oh yeah, there was. Great. How many kilowatt hours are required for a kilo of H2 per? If you're using PEM, yeah. So we generally calculate between 55 and 60 kilowatt hours for the electrolysis itself, and then you have to add on things like compression and auxiliary power consumption in the system. So yeah, 55 to 60 is general. It's going to be depending on the manufacturer and what they can make. So I don't have one answer for that, but yeah, it's a lot of energy per kilo. The efficiencies can range from 60 to, if you're using something like a solid oxide electrolyzer and steam as input, the efficiency can go all the way up to 85, 90%, in which case, yeah, that's ideal. But is there any specific feasibility study by Greenstad on building a hydrogen hub in Trincomalee? I'm not sure about Trincomalee. Sturla, if you want to comment.
Yes, we are working on the east side, and there is announcement to come later on, but we are working on it. I can't say more about it at this point.
Yeah, try to cover every
where we are going to work together, and also all the university that has joined us when we are now setting up a center of excellence in hydrogen in Sri Lanka, where we are inviting colleagues, universities abroad to participate in building up the skills and the new generation of engineers who is going to develop the next generation of technology and operate these facilities and take care of safety as well. So thank you everyone, and thank you Uda for this excellent presentation.